Hello folks. Welcome back to second part of our problem, how to identify glomeruli in human kidney tissue images. If you haven't watched the first part yet, please watch it first to build the background information required to understand this video. To moving forward with modeling part, we start with setting the cross-validation strategy. Our cross-validation strategy is fairly simple, it's 5-fold cross-validation, but here we make sure of one thing, that for each fold 50% of the data should be masked and 50% of the data should be unmasked, which will help our model not only to predict well but to understand the difference between masked and unmasked area. To talking about architecture, the architecture used as our custom architecture which was defined by the winning team, it uses the famous UNet but with pre-trained layers of Segmentation 101 as encoder and a learnable decoder followed by CBAM, hypercolumns and deep supervision. I know it might be very confusing, so let's break them down one by one. To UNet is fully convolutional network aka FCN, which was mainly invented to deal with biomedical images where we wanted not to classify only but to identify the area of infection as well. Currently it's very well used in semantic segmentation. To just a recap, that semantic segmentation is when you mask out the objects in an image, so you input an image and the output is an image too, but with masks identifying the objects. Back to UNet, the architecture contains two paths. First path is the contraction path, also called as the encoder, which is used to capture the context in the image. The encoder is just a traditional stack of convolutional and max pooling layers. The second path is the symmetric expanding path, also called as the decoder, which is used to enable precise localization using transposed convolutions. Thus it is an end-to-end fully convolutional network, FCN, because it only contains convolutional layers and does not contain any dense layer, because of which it can accept image of any size. There are many operations defined in this architecture and we won't go in much details, but remember that intuitively, the encoder learns what information in the image however it has lost where information, and the decoder recovers the where information, that is precise localization, by gradually applying upsampling. To get better precise locations, at every step of the decoder we use skip connections by concatenating the output of the transposed convolution layers with the feature maps from the encoder at the same level. Also a fun fact, because of this architecture has a symmetric U shape, that is why it is named UNet. That was a basic level introduction of UNet. If you want a separate in-depth intuition behind UNet, please comment below, I will make a separate video on it. Before moving to say ResNext, let's have a quick look at ResNext. It is a variant of famous ResNets which has the same skip connection strategy, but it follows a new strategy called split transform merge, which means we split the process, transform the features and then merge them, hence it has much parallel stacking layer rather than sequential layers. To say ResNext is a variant of ResNext that employs squeeze and excitation blocks to enable the network to perform dynamic channel-wise feature recalibration. So basically what I meant is, the squeeze and excitation block is an architectural unit designed to improve the representational power of a network by enabling it to perform dynamic channel-wise feature recalibration. The process is fairly simple. First, the block has a convolutional block as an input. Then, each channel is squeezed into a single numeric value using average pooling. And then, a dense layer followed by a ReLU as activation function adds some non-linearity and output channel complexity as reduced by a ratio. Again, another dense layer, but this time followed by a sigmoid activation function gives each channel a smooth gating function. Finally, we weight each feature map of the convolutional block based on the side network, the excitation. So that's a short and abstract overview of say ResNext. Now let's talk about how we combined it with UNet. So the idea is very simple. You have saw the UNet architecture. It is nothing but the convolutional process. So what we did, we first loaded the pre-trained weights of say ResNext for each of its layer and replaced the UNet layers with them. Simple as that. So now we won't start our training from scratch, but we will be having some prior learned weights that actually helped us in improving. To explaining the decoder part further, the decoder also contains the convolutional block attention module aka CBAM. Basically here we try to give more attention to useful informations like the area which might contain the mask, so for that we have two processes, first the channel attention module and secondly the spatial attention module. So channel attention module tries to capture the channel information which is passed from our UNet. It takes the features, applies the pollings, pass it to multi-layer perceptron, obtain a linear representation which contains information like how much attention should be given to particular channel. Then we have the spatial attention module, which tries to capture the high-level attentive representation after getting the features from last module, that was channel attention module. So with this process we have much better features now. 2. We will apply hypercolumn on these features. The idea is the information we have extracted just now might be too coarse spatially to allow precise localization, as it has went through multiple convolution process. Hypercolumn at a pixel is the vector of activations of all CNN units above that pixel. Which means, the spatial location information can be brought from earlier layers, and have a more accurate prediction result. So we have tried to brought that information from our decoder layers. To finally, we have deep supervision. The idea is taken from this paper. It's fairly simple that we supervise the features we have learned so far, and we have achieved this using the one-dimensional convolutional layer on each layer of hypercolumn decoder. So as we had 4 layers to work with deep supervision we will still have 4 layers, but those features will be more deeply supervised and the features will be very well transformed. One more step in our network includes classification, which we will discuss in details in next section. You might be wondering why we made such a complex network and why it actually worked. Well, as mentioned in previous part, the data is very huge and there is so much information to capture. That is why a very complex architecture helped. So starting off with loss functions, we used several losses at different points. So for mask loss, to see if prediction mask is similar to ground truth mask, we used binary cross entropy along with lowest hinge loss. To remember, we used deep supervision in our model. We got separate output mask for that as well, but this is only for images having at least one mask, so we just want to make sure we have captured the in-depth features and we are able to draw a fine boundary for the mask and without wasting or optimizing the model for non-masked images. We are using the same loss combination as last one, but we will be multiplying it with 0.1 before adding it to our total loss just to control its effect. You might remember we added a classifier in our model. Basically, that classifier will simply be predicting if a given image has a mask or not, so it's simply learning the difference between masked and non-masked images in order to avoid false positive in future predictions. You already know about binary cross entropy loss, and how are we using it here? We are simply taking pixel to pixel comparison and taking a log on the loss. Simple is that, but what about lowest loss? Let's have a quick discussion about it. Well, basically, it's a convex surrogate loss function for submodular losses. There are 2 important terms to understand here: submodularity and lowest extension. Submodularity is a property of set functions which comes up very often in several areas of computer science. Many problems in combinatorial optimization and machine learning have submodular structure. And the lowest extension is a very useful construction that can be used for submodular minimization. The lowest extension of a submodular function is always convex and can be minimized efficiently. The minima of the lowest extension can be used to find the minima of the submodular function. And our lowest hinge loss based on the definition of lowest extension, which leads to big O of p log p complexity with big of p oracle accesses to the loss function to compute a gradient or cutting plane. So as a result, with this loss function, the author have developed the first tractable convex surrogates in the literature for submodular losses. To compute this loss is fairly simple. We first compute the errors of the predictions, then we compute lowest extension with respect to sorted errors and take gradient of it, and we compute the loss by dot product between error vector and gradient of lowest extension. If you want to know more about this function, please refer to this paper. Link in the description. As mentioned earlier, the solution is taken from the winning solution of the Kaggle competition, HubMap Hacking the Kidney, and the metric used was dice coefficient, and it placed him on top of the leaderboard. You can find the complete code on GitHub of the author. I will attach the link in description. If you want me to make a separate video explaining the code, please let me know in comments. So folks, thank you so much for watching. Please consider subscribing if you like these type of informative videos. You can also request for something in comments. Thanks.